Welcome back to the enolates chapter. This is slides 30 to 34. This is the end of the enolates chapter, and if you kind of scroll through the remaining slides, you'll see that there are no new flashcards. Most of this is sort of putting what we've learned in this chapter into perspective and giving you some examples in real life about these alpha-beta unsaturated systems and other enolate type chemistry that's important. So sit back and watch as we go through some examples. The first one I wanted to talk about was glutathione conjugation. And this is a process that glutathione conjugation for this slide. Sorry about that. This is the slide 30. And this one shows how we can get certain compounds that enter the body, for instance, like morphine. And in the next slide, we're going to see acetaminophen. The metabolic pathway to excrete these compounds so that they don't wreak havoc in other ways is to go through a pathway leading to mercapturic acid. So glutathione is shown in this box, and the key component here is this sulfur group. That sulfur is primary, so you might think, well, there's an amine here, and amines are great nucleophiles, but sulfur's a great nucleophile as well, and this one's primary. So it's a lot easier to, from a steric hindrance perspective, go after things. The nitrogen amine at the other end is actually secondary and perhaps a little tougher to work with because it's, a little bit less exposed. So this sulfur nucleophile is looking to do just that, be a nucleophile. And so when morphine enters the body, it goes through a metabolic oxidation process where this alcohol is oxidized to a ketone. And then at this point, you can see that we have an alpha beta unsaturated carbonyl. So at this point, the sulfur, which is considered now, you guys know, a soft nucleophile, it is going to do a 1,4 addition at the beta position. And then under the aqueous media, the enolate that forms collapses with a proton just to put a proton at the alpha position. So once this glutathione conjugate has been made, in a few more steps, it's ready to be excreted by urine. Likewise, you see similar things with acetaminophen, right? So glutathione reacts with acetaminophen or Tylenol, which further reacts to form water-soluble mercapturic acid, which can then be excreted by urine. So again, we see the sulfur as the nucleophile. This one's a little trickier to see, but it makes sense, okay? Acetaminophen is metabolically oxidized, and interestingly, right, the aromaticity changes and you end up with this keto system. But also notice it's kind of like an imine. So which is it? Is it relative to the carbonyl? Is this the alpha and this the beta? Or vice versa? Is the carbonyl-like system the carbon double bond nitrogen, whereby this is the alpha and this is the beta? Well, think about what you would be doing. When you attack one of these carbons, the electrons are going to flow up to the heteroatom. So you're either going to form, I'll draw it up here. The enolate, where you've attached the sulfur, right? And so you get this enolate, or you attack the other side, and what you'll see is that, do you notice how if I attacked the beta position relative to the nitrogen, if I do it this way, the negative charge ends up on the nitrogen. It makes like a nitrogen enolate, right? An enamine. that negative nitrogen is further stabilized by the withdrawing group and by resonance with the neighboring carbonyl. If the oxygen ends up on the oxygen, if the negative charge ends up on the oxygen having attacked the beta position relative to the carbonyl, then the O- is sort of outside by itself, and it alone is trying to stabilize the negative charge. So the most thermodynamic, most stable option is for the sulfur to attack the beta position as it relates to the carbon double bond nitrogen, not the carbon double bond oxygen, because the negative charge that results can be further stabilized by resonance. So that's why we see the sulfur attach to the beta carbon relative to the nitrogen. And then again, once it has done so, further few more steps turns into mercapturic acid, and then it's able to be excreted by solubility through our urine. This reaction, actually, I was taught this reaction when I was an undergrad, and we had to learn it. But as I got older and looked into it, I realized nobody uses this really anymore. Nobody really does Robinson annulations. Doesn't take away from their utility and sort of the importance of its discovery, but it's a really important discovery, and it's worth noting and kind of looking at. But I wanted to point out to you that nobody really uses it as written anymore. It was discovered in 1935, and it's called the Robinson annulation. And if you look, it's these two molecules, and what you end up with is a very important 6,6 bicyclic structure. And what I want to point out to you is the fact that you've got these two bicyclic rings, and importantly, you have the alpha beta unsaturated system right at the bridgehead of the bicycle with a carbonyl right next door, right? Let me scroll all the way back to the first slide when we started this. Notice that lovastatin has a 6,6 system bicycle with the double bond right at the bridgehead, and you can see that perhaps the methyl group could have come from having attacked a carbonyl and then reduced it away. So you can start to see that the 6,6 system with the double bond at the bridgehead, you actually see this motif a lot in important molecules, both biologically or for pharmaceuticals. So it was a really important discovery to learn how to make these in a laboratory. So this is why I want to show it to you guys, but you can sit back and enjoy the process of how this happened. And we'll talk about why the yields were, under 30%, which is what makes this not very useful, from an efficiency standpoint. So what Robinson found was that when he mixed two molecules, like the two shown, what you get with base and heat for a long period of time is, first, you end up forming an enolate. And because it's heat and NaOH, you're going to form, you're in equilibrium conditions because you're not using a really strong base. You're using a small base, so you're going to favor the thermodynamic conditions. So the base is going to form an enolate. Now, just to help you guys along, let's number this system. The carbon 1 in the product is most likely carbon 1 here because of that methyl group sticking out, okay? And that's all I'm feeling comfortable doing right now. Next, we introduce our alpha beta unsaturated carbonyl, and we have the enolate do a 1,4 addition. So I just showed you the acid-base chemistry. That was the first step. And now we're doing a 1,4 addition. Let's draw the product of that. okay? Where this is probably still carbon 1. Okay, now if this enolate, as is, collapses, you would form a bond between that carbon and that carbonyl. Count the carbons here. 1, 2, 3, 4. There's only 4 atoms between the carbonyl, the blue carbonyl, and the carbon enolate. So if it collapsed and did a 1-2 addition at this point, you would form a 4-membered ring. That is not the best case scenario, right? We know 4-membered rings have a lot of strain. But we also know that there is an equilibrium set up. Even though it's favoring the enolate shown, there is an equilibrium under these conditions between the kinetic and the thermodynamic enolate. So what's probably happening is that a little bit of the kinetic enolate exists, and now the carbons of interest are the enolate at the other end and the carbonyl for a 1-2 addition. If you count the atoms between here, you've got a 1, 2, 3, 4, 5, 6 distance. Now, this is so much more plausible in doing our 1-2 addition. So the enolate comes down, the carbon minus attacks the carbonyl in a 1-2 addition, and we are now, with that being carbon 1, O minus. Let's number these 2, 3, 4. Okay, so we know this is 1, and we know 1 is connected to 2. Oops. 1 is connected to 2, 2 to 3, 3 to 4, right? 1, 2, 4 is connected to 5, so 5 is now connected to 6. So we know the carbonyl is 6. 1 is connected to 6, and then basically we have a, oh my gosh, I'm so bad at drawing this. 2, 3, 4, 5, 6. We now have our 6-membered ring off of our system. Let's see what else. On carbon 4, we now have the double bond oxygen. Carbon 5 is attached to 6. 1 still has the methyl group. So we're pretty much there. Let me just turn this so you guys can see how this relates. After quenching, because we have water present, right? Because NaOH is grabbing protons, so there's water. We can protonate that. So this is carbon 6, 1, 2, 3, 4, and 5. And now we're basically, after this 1-2 addition, with the heat, we are further condensing it. This is like the aldol condensation, and doing the E2. So I should probably add plus E2 after the 1-2 addition. Right, so here's our 1-2 addition. 1-4 addition, we have our E2. And so now another equivalent of base, OH minus, can grab the proton and kick off the OH minus. Adding more OH minus to our system. And giving us the final product. So really 1, 2, 3, 4, 5, 6. Now we can number in confidence, knowing where everything came from. 6 was actually the carbonyl we started with. Is that right? No, sorry. This is 6. This is 1. This is 2, 3, 4, and 5. There we go. Okay, that's a lot. That's really putting it all together, right? So we got acid-base chemistry forming an enolate. The enolate does a 1,4 addition. Now we've got isomerization of our double bond through thermodynamic kinetic conditions, and only the kinetic enolate is the one that ends up giving us a productive pathway because that forms a 6-membered ring. Once that forms, the OH is protonated. This is technically an aldol reaction, and then it turns into an aldol condensation because we heat it and you further dehydrate, take off a proton, form a double bond through elimination, and expel the OH minus. So why do you think that the yields were so low? I want to draw your attention to this reaction right here. That is the problem. So yeah, we get 30% of this product, and Robinson focused in on that, but he probably got a lot of other types of products. Do you see the problem with this reaction, given the 1,4 additions we discussed? The key, right, is that enolates, we learned, regular old enolates with just one carbonyl are hard nucleophiles. So the most prevalent thing was probably the enolate attacking the carbonyl in a 1,2 addition, not a 1,4 addition. And therefore, you don't get this product if you go via the 1,2. Hence, this reaction is not very efficient. But it does lead to something very cool. And so what folks did was they said, well, how can we make the enolate softer? And so if we can make a standard enolate soft, then we can open up the opportunity for a 1,4 addition on a regular enolate. We won't always have to have a 1,3 dicarbonyl system to do it. And so this is where we can use some of our old chemistry. And this is FYI. Notice I did not put it into a flashcard form. This is just for you guys to kind of enjoy why you learned what you learned and why it's important to us organic chemists. So if I started with this ketone, notice that I only have one viable alpha carbon with hydrogens on it, right? The other side is a tertiary, well, quaternary carbon with no hydrogens on it. So Gilbert Stork, came up with this really cool way of sort of tricking the enolates to become soft nucleophiles. So let's start here. Let's start with taking our ketone and reacting it with a secondary, well, I'll just draw one out as an example. A secondary, let's do it, dimethylamine, okay, with a little bit of acid to catalyze it. And if you guys remember, a secondary amine and a ketone form an iminium system. And then, if you recall, mechanistically, so this gets protonated, the nitrogen attacks 1,2. This is back from the ketone aldehyde chapter, remember? We're driving the nitrogen on, we're driving the oxygen off, and ultimately you end up at this iminium system. And then, because the nitrogen was secondary, do you guys remember how we couldn't just deprotonate the nitrogen and be done with it and stay with the imine? Because you can't deprotonate it, it has 2 methyl groups on it. So what did we do? Didn't we go for the alpha carbon position? Didn't we use the nitrogen as a base? And simply deprotonate the imine at the next most acidic position, which is the alpha position. See, we were doing this before, but we weren't really talking about it in that same way. And look what we were forming. We're forming an enamine. Enamines are like enolates, but they're stable. So here's an enolate, right? It's an intermediate. Here's an enamine. It's a stable functional group. You can isolate the enamine and take an NMR of it, run a TLC on it, purify it, and keep it in a vial and store it. So you got an enamine. Enolates are intermediates, and you need to react it with something immediately because it's a charged intermediate species, but enamines are stable. Enamines are also soft. Enolates are hard. Right? You have a charged electron cloud here. Here it's not charged, so it's a softer nucleophile. Now we can take our enamine and react it with our alpha beta unsaturated system. Treating it like an enolate, the nitrogen can kick its electrons down. The alpha carbon becomes the nucleophile, and you actually get your 1,4 addition. Here's my blue carbon. Let me number 1, 2, 3, 4, 5. 5, 4, 3, 2, 1. Double bond to nitrogen. We're back at the iminium system with the T-butyl group on the other side. At this point, we then work it up under aqueous conditions, and lots of stuff happens here. We hydrolyze and quench. So on the one hand, the acid, all the acid-base chemistry that we need is given so that the enolate just gets protonated by the quench. And the iminium system is attacked by the water. So remember, I tried to get you guys to see that imines can be hydrolyzed back to their carbonyls, right? If we drive on the water, ultimately water in, nitrogen out, imines convert back to carbonyls. You have a flashcard for that. And without going through the whole mechanism, you guys can try writing that out on your own. The imine converts back to, right, here's carbon 1. The imine converts back to the carbonyl. Carbon 2, carbon 3, carbon 4, carbon 5, and the carbonyl. So what it looks like is it looks like we added an enolate to a beta position, when really we tricked it into going there because we had to make it soft. Enolates, by nature, are hard nucleophiles. So you can use an enamine if you want your enolate to attack at the beta position, but then you have to convert the enamine, or the iminium system you end up with, back to a carbonyl to make it look like that was what you did all along. The Stork enamine synthesis actually solves the Robinson annulation problem. And now you can do this exact reaction by changing your carbon 6 into an enamine. And in doing so, you get much higher yields, like up in the 80 to 90% now for the molecule shown, the bicyclic system. Another cool biochemical enolase reaction is, which is also important in glycolysis, has to do with enolases. So enolases are an enzyme, and here's a 3D model of a metalloenzyme known as phosphopyruvate hydratase. It's a metalloenzyme. There's a metal that sits right in the center. And it's for the catalysis conversion of 2-phosphoglycerates, 2-PG, to phosphoenol pyruvate, PEP, PEP. You can see the enol form in here, enols. The ninth and penultimate step of glycolysis. So when we have this PG, here's the 2-PG molecule, you can see that. It binds to the alpha enolase. Okay, so you can see this nitrogen here. The amine acts as a base. So the enolase amine is our base, and that's what deprotonates at the alpha position. And that's what empowers the oxygen to be negatively charged. And those oxygens are highly attracted to the magnesium in the enolase. The magnesium is the metal that's in the metalloenzyme. Once here, this stabilizes the negative charge on the deprotonated oxygen while increasing the acidity of the alpha hydrogen. The enolases 345 deprotonates the alpha hydrogen, and the resulting negative charge is stabilized by resonance to the carboxylate oxygen and by the magnesium ion cofactors. So that's what we see in the middle. This proposed mechanism for converting the 2-PG to phosphophenol pyruvate, which is the PEP molecule, is based on the use of isotopic probes, studies of crystal structure, and kinetics. So this has been studied to understand how this is occurring. But here's the enolase, and you've got the carboxylic end. So what's happening here is that I can show you how this works. We have to reform the double bond. This is a weird step. This comes down, and then this gets protonated. So you are losing, this OH is lost as water. Oh, I have it up there, as water. And the enolase leaves as an O- that's conjugated. It's a carboxylate, right? It acts as an acid. The OH, it gets protonated by the acid and becomes a good leaving group, which is why the enolate can collapse in this fashion. So that's kind of cool to see our enolates at work, right? Our alpha protons getting deprotonated so that it can actually form strong bonds to magnesium, which is the metalloenzyme. And then you can see it's collapsed to lose water and form the PEP molecule. All really interesting stuff. So the enolate chapter, alpha carbon chemistry, is something to be aware of. And as I mentioned, I am going to be focusing on bases that you will be comfortable with, sodium methoxide, sodium ethoxide, and LDA, to really say, okay, I'm doing enolate chemistry. Because I understand that it can be a little confusing. Like, when do I do enolate chemistry and when do I make that nucleophile do a 1-2 addition? I think that's the biggest hiccup in all of this. Trust me, I will make my practice exams as well as the real exams very clear in my motives for what mechanism I want you to employ. So good luck, happy practicing, and stay tuned for amines.